we will see one more application of Ampere's law. That means the magnetic field due to, that means H due to the magnetic field intensity due to infinite sheet of current. Okay, so let us consider an infinite sheet of current. It's a big sheet, so it is an infinite sheet which is carrying a current. So let me draw it a little bit bigger. So this is an infinite sheet which is carrying the current. So we can first define what is the axis. So in which axis actually it is carrying the current now. So you see here it is carrying the current in this direction. Okay, it is carrying the current in this direction, and we can assume that this direction is the y direction, for example. Okay, let us consider this is my origin. So this is my origin. So this can be the y direction, and this is the x direction, and this is my z direction. Okay, so the unit vector in the direction of y is ay, the unit vector in the direction of x is in the direction of x is ax, and the unit vector in the direction of z is az. Now it is carrying a current with uniform current density. So it is carrying the current with uniform current density, so it is denoted as vector k. So in this case the vector k is given as ky into ay. So this is showing the magnitude. So this is showing the magnitude, and this is showing the direction. Ay is showing the direction. Okay, so I hope it is clear to you. And this is having the unit ampere per meter. So along the length actually, so along this length, so this is in meters, for example. So if it is in meters, so this k is actually showing you how much ampere is there for unit meter. Okay, how much ampere is there for unit meter. So this is what the ky is showing actually. So this magnitude is showing. Now we will see what is the magnetic field intensity above this. For example, if we are viewing it from the side, so the sheet will be looking like this. So what is the magnetic field intensity here? What is the magnetic field intensity here? Okay, and what is the magnetic field intensity here? So everything we will be finding out by using the Ampere's law. So for that, first of all, we need to consider some symmetrical loop. Okay, so how we can consider the symmetrical loop? So I can consider a symmetrical loop like this. So let me choose a good color suitable for this. So I can consider a symmetrical loop like this. My loop is starting like this, then it's going down. Okay, so now it is in the other side. For example, if you are viewing from the side, so this is your surface. Okay, this is from the side view. Then the loop will be like, it will be penetrating here. You see it will be penetrating the surface. Okay, then it is going there like this, and other side. So this is what happening now. Okay, so we are considering a loop. So it is going down, then it is going in this direction, Okay, let me draw it properly to avoid the confusion. So it is going in this direction, then it is going up. So this is the loop. So we will consider this loop. So we can see here what are the directions of this loop. So first of all, we will mark the direction. So you see this direction is giving you actually ax. So what is this direction? It is giving you actually, you see you are moving opposite to the direction of z, so it is nothing but minus az. And this direction, you see you are moving opposite to the x, so it is nothing but minus ax direction. And this is nothing but you are moving in the direction of z, so it is in AZ direction. So I will consider this as 4 pieces. So it for easiness. So this is the line 1, this is the line 2, this is line 3, and this is line 4. Okay. So what does the Ampere circuitous law says? So the Ampere circuitous law says that the integral, the closed loop integral of h dot dl will be equal to I. Okay. So in this case, how can I get the total, how can I get this total closed loop integral? So let us consider my h in this direction. Okay, let me choose this color, some other color is better color. I will choose it, I will use white. So let me consider the direction of h in the direction of x is given as hx. Okay, so this is the magnitude is hx. Okay, and in the direction of z is hz, in the direction of x is hx. Okay, so this is what we are going to consider. And you know that whenever there is a current flow in this direction, we have a current flow in this direction, so then the magnetic field will be looking like this. Okay, so the magnetic field will be looking like this. We have already seen this thing. Okay, so this is the closed loop. So you cannot expect any magnetic field like this. Okay, so we can avoid that possibility initially itself. So you can see that the magnetic field is moving to the current is moving in the y direction. So you can have the magnetic field, you can have the chances there, you can have the magnetic field in the z direction as well as in the x direction. Okay, so the magnetic field, this hx and hz are just the magnitude. It is not having the direction now. Okay, I didn't show any direction. This is magnitudes in x and z directions respectively. Okay, so this is what I want to tell you. Now we need the vector h. So I will take the first case, the first loop L1. So in that direction, what is h? So what is h in that direction? So you know that it is hx, and the direction, you see that it is moving in the direction of ax, so hx into ax. And what about in the loop 2? It is nothing but, you see the magnitude is hz and it is moving in the minus az direction, so into minus az. Now in the loop 3, not loop actually, in the line 3, sorry, in the line 3 actually the magnitude will be same as that of hx because of the symmetry. So it will be like hx and we will be moving in minus ax direction, so it will be into minus ax. Next you see here again we are moving in the z direction, so the magnitude will be in the line 4, actually the magnitude will be hz, but the direction also, direction is like az. Now we need to focus on what is the dl. Okay, so you see here this dl is a vector, so we have to see what is that dl. Okay, so this is the magnetic intensity. So these are all the magnetic field intensity. So these are all the magnetic field intensity. Now we will see what is our what is our length L, dl. Okay, so in our case we have the differential piece, this we will consider its dimension is b here, and on the bottom also it is b. So I will show with a different color, it's b, and on the sides it is like here a, and this is also a. Now so this length is a, this length is A. Okay, so I hope it is clear. Now we will see what is our DL in this case. You see the first piece we have B, and B is moving in the direction of AX, so B into AX, isn't it? So next is A into minus AZ. So A into, this is the length, okay. So this is the length, and this is also here also it's the length, okay. So A into minus AZ. Next is like B into minus AX. So the length is like B into minus AX, and the next is like A into, you see the fourth piece L4, it is like A into AZ. So the length is like A into AZ. So I hope it is clear. So what is the closed loop integral? Actually we will first integrate over L1, then we will integrate over L2, then you will integrate over L3, then you will integrate over L4, right? So we need to find H dot dl, and these are all the straight path. So direct multiplication, and you know the total length is B, so the things are very easier. So we can say what will be H dot dl here. So along L1, H dot dl along L1, okay, this will be equal to, you see here Hx into B, this become Hx into B, then you have two things, Ax dot Ax, so this is equal to 1, and along L2 H dot dl will be equal to, okay, this is along L1 and this is along L2. So along L2 it will become minus of Hz. You see here there is a minus here and there is minus here, so minus into minus, so it become A into Hz, okay. Then you have Az dot Az become 1. You can see this Az dot Az become 1. Next is minus Hx into B. So you see here minus Hx, that is minus B, so it become Hx into B. So L3, so integral over L3, this become H dot dl, this equal to, it will be equal to Hx into B. So Hx into B, okay, it's clear. Now along L4, okay, along L4 this is H dot dl will be equal to Hz into A. So Hz into A, okay. So the second one I will write like this, Hz into A. So you can see here that there are common terms like Hx into B and Hx into B. Then you can see Hz into A and Hz into A. So you can see if you take this sheet, you can see that one is on the top. Actually this is like on the top, and the current is moving in this direction. The current is moving actually in this direction, and the other one actually in the bottom, you have seen already, the other one is in the bottom. So this is the term Hx into B, okay. So these are all the terms, these two terms, red color, whatever I have shown in the red color is showing in the Hx into B, and if you integrate it will become 2Hx into B. But there are some terms you can see here. Let us consider the current element here, and this not the current element, let us consider the current density, let us consider the currents, two currents. For example, let's say this is I1 and I2 on the same sheet. Now if the current is flowing like this, you know that the magnetic field will be like this, right? And this will be the magnetic field, and due to the I2 there will be magnetic field, and here we have the uniform current density. So in this case these are equal, actually these are equal. So what is happening, you see here on the right side of this, or on the, if you are viewing from the side like this, you can see that this is going down and this is going up. So you can see, if you focus here in this region, you can see that one field is going down and the other field is going up. So what will happen, the net field, okay, the net field will be like, so because of this, the net field along z direction, in our case z direction, cancels each other. Okay, so due to this reason, we can say that these are all the z direction components. So these z direction components, this is also the z direction component, so this will cancel, this will cancel. So the total integral, so total integral will be nothing but hx into b plus hx into b. Okay, so we have seen that h dot dl is equal to I. So the total integral of h dot dl over the closed loop will be equal to hx into b. Okay, and this is equal to I, not hx into b, 2hx into b, because there are 2 hx into b. So we will be getting hx into b into I. Okay, now this will be equal to I. Now we have the current density. Suppose, so now you should know that we have taken this b length like this. So this is the length b we have taken from the sheet which is carrying current. So here this is the current element, the current is in this direction, and you know the current density, okay, the current density is k, which is equal to ky, okay, ky into ay. So what will be the total current? The total current will be equal to, you know what is ky, so it is nothing but, it is in ampere per meter, and you are considering actually b meters. So what will be the current that you are going to consider in that particular path? So you can see that the total current will be equal to, your I will be equal to, you know what is ky, so just multiply with the length b. So this will be equal to ky into b, or I can say that my 2hx into b is equal to ky into b. So this will cancel each other, so my hx is equal to ky into ky over 2. Now what is the direction? That's what the important question. So you see here in this infinite sheet, this is the sheet. In this case, actually on the top the current is moving in this direction. So if that is the situation, if the current is moving in this direction, that means in the direction of ay, if the current is moving in this direction, the magnetic field on the top, so this is the magnetic field on the top, so it will be in this direction. Okay, and in the bottom, let me use another color, it will be in this direction. So this will be in this direction. So this is in the bottom. Okay, so this is in the bottom. So you can see here that this is the direction. Okay, sorry. Okay, so this is the direction. So hx will be having the direction. What is the direction? It is having the magnitude ky over 2. So what is the direction? It is in the direction of x. So the direction of hx is in the direction of x. Okay, it is in direction of x. So ax is the direction. So how we can generalize this direction? So that's what we are going to see now. Suppose this is the sheet, this is your sheet, and the normal to the sheet is given as an. Okay, so the current is flowing in this direction, that means in ay. Then we have seen that the net direction of the field is like in this direction. Okay, so this is the direction of the field, and the direction of the field is like in ax. Okay, so this is the direction of the field. So how we can get it? So if you are moving y to n, that means ay cross an, that will give you ax. So just imagine you are just rotating y to n, so that will give you the direction. So this is the direction of field. Okay, so what is this ay? Ay is the direction of the current. So we can say that it is the direction, in general we can say that it is the direction of k, and this is the normal to the sheet. So if we know these two things, we can generalize this fact, we can generalize the previous result. Okay, we can generalize the previous result as h is equal to half. Okay, then instead of ky, the direction, instead of ky into ax, because this contains the direction ax and ky is the magnitude, so we will take the vector k. Okay, the vector k, anyways, vector k. Okay, so this is the direction of k, this is the direction of k. Okay, the vector k. So the vector k cross this normal to the surface. Okay, so if you have surface in any angle, suppose you have the surface like this, okay, and the current is flowing like this, so the current will be flowing maybe in this, like this, like this. Okay, this is the direction of the k, and the normal to the surface may be like this. Suppose this is the normal to the surface, then just take, this is the normal to the surface, then just take the cross product between these two, then you will get this angle. Oh, then you will get this angle, actually this is the direction of h. Okay, direction of h, and so the final result can be concluded like this. Okay, so I hope it is clear to you. Thank you. And one more thing, I think that will be also helpful. So in this infinite sheet, you have seen that on the top the magnetic field is like this. Okay, and in the bottom the magnetic field is going like this. So at the corners it will be bending, you know, so here it will be like this. Okay, so this is the structure of the magnetic field in an infinite sheet. So so this is the shape. Okay, this will be the shape. So I hope it is clear to you. Thank you.